We're now going to look at the second manner in which we can experience a force due to a magnetic field. And so that is a force on a current element. And it's worth noting that this is a force on this current element due to some external magnetic field B. Our current is not exerting this force on itself. So what we want to do is we want to utilize that magnetic force equation we had previously, because really all current is moving charge. And we know for moving charge, the magnetic force is equal to the magnitude of the charge Q times the charge velocity U cross with the magnetic field B. So now if we want to relate this to our current situation of a current element, we need to somehow relate current to our charge as well as to the velocity. So let's start by saying that in general, we know that current is just defined as the rate of change in charge over the rate and change of time. So I equals dq dt. And let's also consider some differential length of a current carrying filament. So let's say, for instance, we have some current carrying filament and it's going on in those directions, but we're just going to be looking at considering one differential length here. So let's say we have some dl, and of course we have current flowing there, so that current in that differential length is going to be IDL. So let's say, write out what we're doing here. So this is a differential portion of some current carrying filament. And so of course we're saying that our overall current in this filament is I, and we just happen to be looking at this differential length, and I didn't put a direction, but of course that should have a direction as well, which is going to have some differential current IDL. Okay, so we know we have differential current IDL, and above with our general equation here, we said that our I is just equal to dq dt. So we have I in a different form multiplied by dl. Well, what if we play some games and I can pull my dq out front, and then I have dl divided by dt, and so now I essentially have change in position over change in time, which is of course equal to velocity. So I have dq times u. So what I can do now is I can go back to our original equation for a moving charge, and I can say we have this relationship between dq and u and our current. So if I have a dq here though, that means that I'm going to need to adjust our left side to be df, so some differential force, because again, we're considering some differential element. Okay, so let's write that sort of updated equation. So now we have our differential force is equal to IDL, because remember we said that is equivalent to our dq times u, cross with our magnetic field B. Okay, so of course if we want our total force, what we're going to have to do is we're going to have to integrate. So where are we integrating? Well, let's integrate around a closed path, which is going to represent a circuit where that current I is flowing. So integrate around a closed path, which is representing some circuit with our current I. And so what we're going to get then is the total force on that circuit. So the force on the circuit then is just going to be F is equal to the integral around the closed path L of I dl, so our differential current length, our I is a scalar value, our dl is a vector in this case, cross with our magnetic field intensity B. And so that's our general equation if we're considering some filament of current. But as we saw in the previous unit, we can also have a sheet of current, or we can have a volume of current. And so what we saw previously is we had equivalent differential currents for those two cases. So for our filament of current, we have IDL, and that's equivalent to, in a sheet current, our sheet current density K times the ds, our differential surface. And for our volume current density, that's equivalent to our current density J times dV. And so with that in mind, we can update this equation above to get force equations for sheet of current and a volume current. And so let me just note that if you are looking for a reference on this, you can see page 299, where we initially discussed that in the previous unit. So now all we're going to do is essentially update this term here. So for a sheet of current, we're going to have our force is equal to the integral over a surface times k ds cross our magnetic field B. And similarly for our volume current, we're going to have the force is equal to the integral over the volume of J dV cross with B. So with all of these sort of equations for our force and our magnetic field B, we can come back and we can define that a little bit clearer. So this B term, again, we've talked about it before as being a magnetic flux density, but here we're going to typically refer to this as our magnetic field. So magnetic field B. And so what we can see, I think, most clearly from this equation here is this represents a force per unit current element. So our B is representing a force per unit current element. And that's because, of course, we're crossing that with this current element, this differential current element DIL, and that's giving us our differential force. So again, just sort of an alternate way of thinking of this B, and maybe that gives you a better physical sense of what it represents.